Here we go. Now we're ready. Okay, welcome back, everyone. And beginning always with a little prayer. In the name of the Father, the Son, and the Holy Spirit. O Lord, send forth your Spirit, and we shall be recreated. You shall renew the face of the earth. Amen. Father, Son, and Holy Spirit. All right, so this is kind of the clincher lecture on climate change itself. So far, we have been looking mostly at some evidence on the physical side and the biological side. We looked at the geosphere, the atmosphere, the hydrosphere, then cycles in nature, recycling, human recycling, right? Because we're the only species that actually produces garbage that endures on the planet, synthetics. And then we saw also the energy flow and some creative ideas for alternative energies to get away from fossil fuels. Because the big offender here with regards to climate change is CO2. It's not the only one, but it's one of the major ones because it's a greenhouse gas, right? What does it mean that it's a greenhouse gas? Greenhouse gas, what does that mean? Greenhouse gas. Well, yes, what happens is, so we are accustomed to South Florida in a subtropical environment, so we're not too familiar with greenhouses down here. And in fact, we have a little house in the on campus that we call the greenhouse, but it's not a real greenhouse in that concept. It's called greenhouse because it's painted green. It's a solar station in the forest, right? But a real greenhouse up north is a glass house. It's really a house made out of glass that has plants in it. And those plants stay green during the winters. And that's why it's called a greenhouse. Okay, so winter greenhouse. And here are some examples. Sorry, clicked the wrong thing. Let me go back. Images. All kinds of greenhouses, very creative, right in the middle of snow. Okay. And here is snow and green things inside. Because what happens is light, speaking of light, light goes through the glass or plastic sometimes, kind of clear plastic. And then there's an energy transformation. Some of the energy is transformed into what? Into heat, exactly, into heat, right? So light is one type of energy, transforms into heat, and the heat is trapped inside the greenhouse. So it makes for a warmer micro weather in there, microclimate, and plants can be kept green during the winter, even though there's snow around on the sides, and even the trees have lost their leaves. Do you know what those trees are called when they shed their leaves in the winter? Like this guy back here, right?
Is it deciduous?
Exactly, deciduous, which means that they drop their leaves in the winter. All right. If we were to see a tree like this down here in South Florida in a subtropical environment, we cut it down because that tree is dead. But in the winter, all trees look dead. Up north, they're not dead. They are hibernating. And then they come back in the spring, they start putting out little buds, and lo and behold, the tree is alive and puts out leaves. There's one group of trees, a major group of trees that stays green during the winter, and precisely they're called evergreens, right? Which group of trees is that? They're not deciduous. They are conifers. Right out the window, we looked at the slash pine here. Day canyon slash pine is the one species of pine trees that has adapted to this environment. But typically they are adapted to up north. You know, they have needles instead of leaves. They have cones, woody, hard cones instead of flowers. All that for winter endurance. And also internally, they have resin instead of sap, which is oily, thick, and doesn't freeze in the winter. So they stay green, and that's their leg up, because conifers, pine trees, tend to grow slowly, more slowly than the citrus trees. And their advantage is precisely in the winter that they stay green, as opposed to the other trees that become dormant, the citrus trees. All right. So anyway, greenhouse is what happens in here. Greenhouse effect is essentially a warming effect to retain heat, and CO2 retains a lot of heat, right? CO2 gas, and that warms the atmosphere. So it causes the same effect of, like if you were a greenhouse, a huge greenhouse throughout the planet, as we saw with the movement of the Hadley cells. All that CO2 is moved around the Earth, right? And has the effect of warming the environment, warming the atmosphere. So that changes the conditions toward a tropicalization of the Earth. We'll get into more details about that. So basically, there's a lot of focus today on CO2, because CO2 is a product of burning, and burning mostly fossil fuels. And the problem is that fossil fuels to this day are still the cheapest fuels available, especially for industry and for transportation and so forth. And of course, in a market economy, the industry and commerce is always looking for the cheapest source of energy to run the machinery, because that is an expense of the industry. All right, so today we're going to look at this issue of climate change and who is causing it, and how can we, excuse me, how can we mitigate it, and the impact that it has on humans and on the rest of the environment. So topics within climate change is global warming, and some of the other consequences like polar ice melting, sea level rise, ocean acidification. All this has an impact on the environment, on nature, including human nature. And then also loss of biodiversity. In other words, biodiversity essentially is what? The number of different species that we find in the environment, right? And there's a natural number that if there's an empty niche, as we saw with pioneers, one of the previous classes, pioneers will come into an area and start colonizing. First plants, and then animals will follow those plants. And then many times we don't see them, but they're there. Of course, the other two large groups of living creatures, the fungi and the bacteria, which are also very much part of the natural cycle for recycling decomposed plants and animals, right? So that's biodiversity, and it's expansive. In general, it's expansive. What do I mean by expansive? If there's an empty niche, if there's an empty space somewhere on Earth, likely it's going to get colonized. It's going to get colonized, all right? So you think about this, we kind of take it for granted. But when you think about it, nature tends to take over. Life tends to take over whatever niche is available, according to the conditions that are. Some species are better adapted to a colder environment, some to a warmer environment. So depending on the abiotic factors, what species move in there. But invariably, some species will move in, okay? So with climate change, all of these things are impacted, and there is a net loss of biodiversity. So it's a poverty, it's an impoverishment because there's a net loss of biodiversity. And precisely because of the complex food chain and food web that exists, when some species start disappearing, extinct, then other species will be impacted because they either depend on that species for food, or if they're predators, then other species will overpopulate and so forth because there's no checks and balances. So there will be an imbalance, a disruption of the natural system, which is pretty complex. And in fact, I've mentioned this before, especially when we go out to the forest, the complexity that we see, typically that we see above ground, is nothing compared to the complexity that is below ground. So we really, whenever we look at ecological system. We're looking at two systems at the same time, or they're actually in place, two systems, two ecosystems. One that we see above ground, right? Animals and plants and the fungi and bacteria that they're interacting with each other. But then there's another ecosystem below ground, beginning with the root system, and then all of the animals and fungi and bacteria that live down there also and interact, which is far more complex than we see above ground. At least above ground, there's empty space, right? But below ground, I can tell you, typically there's no cubic inch of soil that doesn't have some creature living on it, whether it's a root or a grub or a worm or bacteria by the millions, and fungi. There are some fungi that cover half a state with their hyphae, with their filaments. They're humongous, huge. They cover immense areas, and it's all on the ground. We don't see it. We walk over it and keep going. But that's part of the ecosystem also. And a lot of what's underground is maintaining what's above ground alive, right? In the interaction. So we have to think at those levels of complexity, and that's what ecology does. So ecology goes beyond just biology, has to incorporate also climatology, has to incorporate soil science, physics, chemistry, geology, so ecology is a much more complex because it's trying to look at the ecosystem as it exists in its complexity. And typically it's interdisciplinary and collaborative. So when we see articles on ecology, has many authors, each one has a specialty. You see that?
So, like for instance, I'm from Colombia. And they said Colombia is a biodiversity country.
Very much.
But that includes the underground already?
Also. No, also includes underground also, which is harder to assess and to quantify, because whenever we dig or we go underground, we're already disrupting the system. At least up here, we can photograph and measure and so forth and be minimally disruptive, all right? But when we go underground, how do we measure that stuff? So they're getting very creative. We're using ultrasound and some techniques to try to penetrate the soil without disturbing it much, so that we see what's naturally occurring down there. A lot of research also being done now with communication between root systems of different species underground at the biochemical level. And functionally, it's analogous to communication, for example. We're not the only species that communicates. We hear birds singing all the time and so forth. Many animals communicate that way. Plants also communicate, but they communicate biochemically. They establish their territories and so forth. So it's pretty complicated. Speaking of Colombia a little bit, in general for South America, what you have is the Andes, which is a high mountain ridge there. And you have the Pacific on one side, Pacific Ocean, the Atlantic on the other. And so you have many different climates, vertical stratification of different climates. You have all the way from snow-capped mountains, the high peaks of the Andes, all the way down to tropical rainforest jungles on the coast, mostly on the East Coast toward the Atlantic and the Caribbean. But on the West Coast, it's very dry because the air that comes in from the east as it goes up the mountain, all that moist humidity is filtered out to become snow and rain on the eastern side where the Amazon basin is. And then by the time the air gets to the west, on the Pacific side, is dry. So there's a huge desert, narrow, but very long, all the way from the tip of South America to the bottom of South America down through Chile. El Desierto de Atacama is a huge desert that is very dry, but it's also very rich in nutrients. So the Pacific coast of South America is one of the richest fisheries in the world, because that desert, when it seldom rains, all that sandy soil washes into the ocean, but also there are a lot of seabirds there that drop their droppings, which are rich in nutrients, in nitrates and phosphates, and all that goes into the Pacific Ocean, which happens to be very deep there also. And the particular currents, oceanic currents, stir that up. And so it starts the cycle of marine, first the phytoplankton, so it's equivalent to fertilizer for lawn and grass, right? The phytoplankton, and then the zooplankton that feeds on the phytoplankton, and then the small fish that feed on the zooplankton, so up all the way up the chain to the large tunas and other large fish. So it's very rich. The bottom line is that the coast itself above the shoreline is dry, very desertic, low biodiversity, right? Very few animals and plants live there. But just step into the ocean and it's the total opposite. It's one of the richest coasts and most biodiverse in the world. It's the Pacific, the South Pacific coast of South America. Okay.
Yeah, I'm sorry. Yeah, I'm going to ask a somewhat complex question.
Go for it.
Probably simplify. It's not complex. It's just I can't frame it any other way.
Yeah.
So, benefit and harm.
Right.
I think it would be basically a human construct. If you look at from the beginning of the course, we learned about natural selection,
Right.
which is a process,
Mm-hmm.
and natural selection, in essence, has no bias. Except
Correct.
for whatever the environment is
Yeah.
for that particular.
Fitness, right?
Right. the
And it's
fitness.
long term also.
Right.
The time scale is long.
So my question is based
General.
on that.
Mm.
We speak of biodiversity, but we think of it almost as something of benefit.
Mm.
Where do we see that there is a benefit versus a harm of biodiversity, or is it would just be natural selection? It doesn't really matter if it's
Yeah.
a diverse environment or a non-diverse environment. It just depends on what's able to thrive in that particular environment.
Sure, yeah. I think the main issue here with climate change and the urgency of it is the rate of change. That the rate of change puts it totally out of the natural rate of change. Because as you mentioned, it's true, selection is hammering down all the time, right, upon species in different ways, and some adapt better than others. But there are cycles that are going on, and we've had mass extinctions before on Earth that have totally been out of our hands. For example, the big one has been the dinosaurs were wiped out just by a meteorite that fell on Earth. All of a sudden, boom, we got hit, and that was about 65 million years ago. So that caused a huge mass extinction globally, great loss of biodiversity. But at the same time, it opened up niches for new species to develop, including the mammals, because as the Earth also turned colder, then there was an advantage for warm-blooded for maintaining internal temperature with hair, right? And so mammals flourished after that, and they weren't being wiped out by the dinosaurs that were just totally voracious. So typically, sometime after a mass extinction, there will be what is called a expansive radiation, which is an increase in biodiversity. So we have these cycles. Only that these cycles typically occur in geologic time, which is thousands, hundreds of thousands, or millions of years. The problem we're seeing now is that within decades, the climate is changing drastically. And so nature just doesn't adapt that fast, or many species don't adapt that fast. Okay, so that's why there's this idea that it could be cataclysmic, because it could trigger a bunch of things at the same time, and it would be overwhelming. But anyway, we'll get more into it, and I can see this topic has been around quite a while, but I also want to do, what I want to do here is always making distinctions so that we can speak more precisely and accurately about the topic, okay? And so what I want to say just to start is that there has been climate change on Earth all the time going on, but again, in geologic time. That we can tell, estimating going back, because the thermometer has only been around for maybe, I don't know, I'm going to guess a couple of centuries or something like that. But how do we measure temperature in thousands of years or millions of years ago? We can only measure it indirectly, right? Looking at some evidence, and a lot of it is ice cores and the CO2 bubbles that are trapped inside the ice core over millennia. But anyway, to crunch it, here's one graph that I consider very informative, that points out in the second half of the life of our planet, the past 2.5 billion years, all right? So this scale is in millions. typically the horizontal axis, which is the independent axis, right? It generally is in time when we look at geologic processes. And so these numbers are in millions of years. So we go back to 2,400 million years. That's 2.5 billion years, which is about half of the Earth's life, the Earth being about 4.5 billion years. All right. In the past half life of the Earth, there have been, at least that we can tell, 5 ice ages that have occurred, 5 glacial periods, where mostly the northern hemisphere has been covered with a sheet of ice. Now, when we talk about glaciers and ice ages, first to consider that most of the land on planet Earth is on the northern hemisphere, right? See, if I can just get a map. I don't know if this is gonna work. Let's try it. Maybe. No. Well, just consider that most of the landmass on Earth is in the northern hemisphere. The southern hemisphere has more ocean, the South Atlantic, South Pacific, and the Indian Ocean, except for Antarctica at the very bottom, looking from our perspective, which is a continent, all right? So most of the landmass really is on the northern hemisphere, and so ice ages have covered typically the northern hemisphere. And we're not talking about 10 or 20 feet of ice. We're talking 1 to 2 miles of ice. It's just huge. It's almost bewildering to consider an ice sheet, right, of 2 miles high of thickness. And also they move back and forth over geologic time in hundreds of thousands of years, and they grind anything that's underneath, which is essentially the Earth, down to the bedrock. Okay, and so these are ice ages. It's pretty intense, and there's massive destruction of life on the planet when the ice ages occur. And typically what happens is the animals and the plants generally kind of move ahead of the ice sheet, and even plants can move that way in the sense that it's the next generation that keeps germinating in front of the ice sheet, all right? Because again, we talk about thousands and thousands of years, so we have several generations of plants going forward that way. And I've explained to you before, that's how these pine trees got here, because they are originally from up north, the slash pine, the Dade County slash pine. Anyway, there's evidence of this. And of course, this has happened over millions of years, and we humans have not been producing CO2 for millions of years, right? So we essentially had nothing to do with these ice ages. So there has been climate change on Earth all the time, ever since we've had water capable of freezing, right? Because at first it was mostly vapor, it was too hot to have liquid water, but eventually when the crust cooled down enough to have liquid water, then we got into these cycles. And there's a cycle there, but it's a very long range cycle. Now, these are some of the things that can affect and can trigger an ice age. Yep, go ahead.
It was on the previous slide.
Yep.
On the interpretation.
Yep.
So the 50 degrees Fahrenheit is the average Earth temperature.
Right.
And when we get to the end where it says today.
Yes.
So are we in an ice age now?
We're in an interglacial period. All right, we're interglacial, and it's anybody's guess which way we're going. If we're going toward tropicalization or winterization, we're getting there. You'll see some slides. I'll show you in the past 500,000 years, we've had 4 ice ages that are more significant to our particular situation.
One more question.
Mm-hmm.
Why is the scale, the lowest scale level 50 degrees Fahrenheit? Is that the lowest measure of
Yes,
potentially available?
That's right. So these are averages. This is definitely an average. Also keep in mind that, as it mentions here, the horizontal axis, the time scale is not to scale, right? Obviously, from 3 to 100, and then You can see 260 to 350 here. It's not to scale, it's a logarithmic scale. That's one thing. But also, yes, this is the lowest average that they could find on that measure, but it's an estimate. It's going back. This is what is called paleoclimatology. It's an emerging field, paleoclimatology, to try to study the climate, the ancient climate, going back millions of years. Okay, so it's not an exact science. All right, so these are just some events, natural events of Earth that can trigger a winterization, that can trigger an ice age, right? And they are cyclic. For example, going around the sun, that's called the eccentricity, all right? So typically that's once a year, and that's the eccentricity. Because it's not circular, we know that the orbit of the Earth and many planets around their sun, around their star, is not totally circular. So it's not an even radius area, it's an ellipse, right? It's an ellipse, so it's displaced. One time we're closer to the part of the year, we're closer to the sun, and another part we're further away from the sun, and so forth. Then the obliquity is the actual angle, because the Earth, again, is not, the axis of the Earth is not vertical, it's slanted. Forget how many degrees, but it is slanted. Not only is it slanted, it's also wobbling. All right, and that's what's called the precession. Not the procession, but the precession is the wobbling of the axis. And that wobble also has its own cycle. Sometimes it wobbles more, sometimes it wobbles less. You can see that that's a very dangerous thing. I think some of us are old enough to remember playing with tops. I don't know if you remember tops, right? It's a little conical piece of wood that has a metal tip, like the tip of a nail or something like that. And then you put a rope around it and you throw it and pull back, and the thing starts spinning. That's a top. Or como se dice en español, there's a name for it. Un trompo, the trompo. Anyway, the top starts spinning. If you do it fast, it will spin very nicely, vertical, but as it starts losing spin, right, momentum, it starts wobbling. So eventually topples over. Okay, so this precession of the planet, of our planet, is something to keep in mind, because when that wobble starts getting too much, we may spin out of orbit. So it may be a few million years from now, so we may see it from upstairs, but it may happen at some point. It's precarious. The whole issue of the Earth is, as stable as it looks, it's precarious. Then also within the Earth itself, at the level of the crust, as we saw, this whole issue of plate tectonics and continental drift, that also has an effect. If you have a continent that is one time toward the poles and another time toward the equator, well, that has a difference on its temperature range and so forth, okay? Volcanic activity, like the Ring of Fire, all around the periphery of the Pacific Ocean. And also the oceanic currents and the atmospheric currents, like the Hadley cells and convection currents and all that we saw earlier. All these are natural phenomena that can trigger either a winterization or a tropicalization, depending. For example, these past 3 years we've had kind of drastic weather, not climate necessarily, because climate is typically measured in hundreds or thousands of years, right? With accumulation of weather patterns. But at least the past 3 years, the Earth has seen extreme temperatures of cold and dry, cold and hot. For example, there have been floods in one area and droughts in another area and fires and so forth. And it's attributed to a phenomenon precisely in South America of La Nina, right? It's called La Nina, the girl, which is contrast to El Nino. El Nino is a phenomenon that occurs there in South America. It starts on the Pacific coast, on the South Pacific coast of South America, generally, and it's around Christmas time, and that's why I call it El Nino. It's a reference to baby Jesus, right, around Christmas time, and generally that's supposed to bring benevolent weather, kind of calm weather, not too drastic winter, not too drastic summer, that's the El Nino effect. It goes up into the stratosphere and eventually covers the whole Earth in a yearly cycle. But La Nina is totally the opposite, because El Nino brings peace, baby Jesus brings peace, but when the girl is born, she is all raucous and rowdy and screaming and yelling and makes a disaster out of the weather. So that's La Nina. All right, so watch out for baby girl. Here she comes. It's in contrast. And we've had for the first time that climatologists can tell in recent history, 3 years back to back of La Nina for some reason. I mean, 3 consecutive years. And that's why we've seen these extreme weathers. Every now and then there's a new fire raging out or a new flood. Just a couple of days ago, it's a huge flood in the Philippines. People trying to pull out. Dozens of people died from mudslides and all that. So that's drastic extreme weather. All right. And some attribute it to climate change, but it's too soon to tell because 3 years, within thousands of years, we don't know. It's going to be noise. Okay, it's going to be what is called noise, background noise. But we have to see the average. All right. So that's as far as natural phenomena over which we have no control, and they cause climate change. So climate change has been with us all the time. The difference now is precisely since the industrialization of Earth, the Industrial Revolution, for the past 200, 250 years, more or less, this fossil fuel burning and the drastic increase in CO2, that's going to be the big challenge. So here's a graph, again, just demonstrating 2 graphs that can be contrasted. One is the temperature on Earth, and this one, thanks be to God, has a 0 represented on it in centigrade. So we know that below 0 is frozen, right? It's ice. And we can see the ice ages here, 1, 2, 3, 4. So if you drew a slope of the line to best fit, you can see that there's a cycle. All right. That's for temperature. And again, this comes mostly from ice cores, estimating the amount of CO2, and we know the heat capacity of CO2 and so forth. So these are estimates. Then to measure the ice volume, which is a scale here, a qualitative scale from low to high ice, you can see that the low ice matches low ice, high temperature. High ice, low temperature. All right. So low temperature, winterization, high ice. Low temperature, another dip in temperature, and an accumulation of ice. All right. Dip in temperature, accumulation of ice. So it's a very nice fit between the 2 graphs. So we can say there's at least an association. There may even be a correlation. Correlation then is pointing toward cause and effect, even though, as a professor in statistics has pointed out, not necessarily correlation may be cause and effect. Sometimes it's hard to tell which is causing which, but obviously, if we're talking about ice, of course, having ice, well, that makes it colder, right? But it needs to be cold to begin with to have the ice. So in this case, we can certainly say that it's the temperature that influences the ice. Then once the ice is formed, okay, that maintains the temperature cold. But we need to have cold to begin with to have ice, natural ice on Earth. All right. Okay, so that's a nice graph there. And this goes back to 500,000 years. So these are the 4 ice ages that are referenced in the past 500,000 years as evidence of natural climate change. Now, into the human, because you can see here, basically, you look at this graph, just look at this area, for example, this area mentally, or maybe I can do this. Let me see. Yes, okay, this might help a little bit. Right. Look at this area of the graph, and look at this area of the graph. Basically, it follows the same pattern. You see here, in fact, here you have a double peak, here's the double peak, here's the double peak. All right, so this is CO2. This is measuring CO2. So in other words, this graph is based on this measurement of CO2, which was following the winterization and tropicalization. But then in 1950, it crossed 300 ppm. You're familiar with ppm, parts per million, all right? Parts per million of CO2 within a volume. In 1950, it crossed that threshold of 300, which in geologic time, at least in the past 500,000 years, had never been crossed. And that includes all the natural phenomena of volcanic activity and all that in the past 500,000 years. Now, keep in mind, the past 500,000 years, geologically, the Earth has been the most stable. We go back earlier than that, the Earth has been not as stable, more plate tectonics, and therefore more volcanic activity, right? But the past 500,000 years, the tectonic plates have been more stable and less volcanic activity. And all of a sudden, it just shot up straight in a very fast exponential growth. And the current is another 100 to 400 parts per million. That's the current level. So this is the concern here, essentially, because the consequence of that is the warming of the atmosphere with the fast increase of CO2 accumulation. This is from NASA that has a lot of data on this. Okay, so let me go to this one first, because here's a little site. All right. From NASA. This is at the global level because they have all kinds of satellites and equipment out there to measure. And there's a graph that I just talked about. And then it has about 6 or 7 major issues of climate change. The temperature is rising, ocean getting warmer, ice sheets are shrinking, melting, glaciers are also disappearing. The snow cover is decreasing on a cycle. The level rising, Arctic ice. I'll show you a little video about this. It's very, very impactful over decades. More extreme weather, like we talked about. And finally, ocean acidification, which I'll talk about also, how that comes about and what impact it has on biodiversity in the oceans. Okay, so that's a nice site there that can be explored in further detail. What I did a few cohorts ago was within the course of the statistics. At that time, I think you're going to be using Python as a computer language. We were using R, which is another free source that you can download, R. And I generated this graph, which is a composite of 5 issues: human population growth in red, CO2 in the atmosphere in black, the average temperature. This is over the past 30 years, and this is from actual data that I found mostly from NASA and other sources that are available on the web. It's for the past 30 years, from 1980 to 2010. Right? So temperature is in green, the amount of ice, the ice level is in light blue, and the sea level itself is in dark blue. All right. So, for example, if we look at temperature, so some of these variables are independent and others are dependent. Of course, the first one is dependent, human population, because we drive that. And also CO2 is dependent and temperature. But these are phenomena that occur in nature. The amount of ice and the amount of sea level, it's certainly an effect, right? Because it's something that is out there in nature. I want to start with the temperature, the green. You notice it goes up and down, fluctuates exactly between summer and winter. So that's why the fluctuation, summer and winter, right? But if you take the slope of the line, if you draw the best fit straight line through the green graph, you can see definitely it's a positive slope, right? And it's a pretty steep positive slope. Look at how it matches so well with sea level rise, which is the dark blue. Again, the curvature on the line, the up and down is summer and winter. That is following the temperature, kind of trails the temperature up and down. But if you draw a slope of the line through the dark green, again, it's definitely a positive slope, right? So it's an increase, gradual increase in the past 30 years. CO2, it's a small increase. You know, it's a small increase, but a small increase in CO2, look at the large increase it has, look at the large impact it has on temperature. Small increase because it is a positive slope, but it's very slow, right? And that small increase in temperature in the past 30 years, look at the impact it's had on CO2, the impact it's had on temperature. So we can see a small increase in CO2 has a big impact on temperature rise. Of course, there's an increase in human population also, because the scale is so small that it's 30 years, only 3 decades, these lines look straight. But if we increase the scale, the lines start curving and they become parabolic, all right? Because it's a geometric increase. In other words, the population is increasing not linearly, 1, 2, 3, 4, 5, but geometrically. 1, 2, 4, 8, 16 is doubling. It's not exactly doubling every year, but it is a geometric increase. It's not linear. It's just that the scale is so small that it looks linear. But if we amplify the time, it will start curving, parabolic. And the same with the CO2. See?
But now, well, you're talking about 30 years, but let's say, would that start curving down now? Because in some parts of the world, it's not going geometrically, but it's going.
It's depopulating. Right, it's depopulation, especially in Europe, and yes. But again, it's a complex system. It's a what we call dynamic system, because yes, particularly the northwestern hemisphere. Northwestern hemisphere is Europe and North America, including Canada, right? So US and Canada. And in general, these are what we call the more industrialized nations, and they are depopulating. We are going into negative population growth of the local population itself. In other words, the European population in general, basically the couples are not having children. They're just contracepting massively and they're not having children. And the United States also, and Canada to some extent also. But that's just the local population as such. You also have to consider immigration and the ethnicities of immigration who are having children, because in Europe, typically it's Muslim countries that are coming in, and they typically have a lot of children. And for US and Canada a little bit, but Canada also is impacted by Europeans, is the Hispanic population, which we also tend to have more children, not as many as in the Muslim population, all right? These are generalities, of course, these are very general statements, but that's the reality of the demographics. And demographics are also long-term, right? In other words, it's not just one generation to the next, but they have an impact, because what they call the baby boomers, for example, that happened in the 50s, well, that large cohort of baby boomers has been moving through the population, and those baby boomers, we're not babies anymore, we're seniles now, okay? And we're going at the upper end of the age bracket, right? And then eventually we'll fall off the edge. But what's coming in is not the same number of people. So gradually what happens is that the overall population ages into retirement, and not enough people are young people are coming into the workforce to maintain the retired by their taxes. So these are the demographics that have an impact on the economy. Anyway, that's with regards to population. I'll show you some other graphs and videos on human population growth that is pretty impactful. But the one slope that is negative here, right? Which slope is the ice? And again, it's a very low melt, but it's real. It's negative, it's very low, it's very, it's a tiny negative slope, right? But it is negative. So it's beginning to have an impact on the ice. This at some point can catapult and start going faster at a faster rate, where it could be, of course, ice melt impacts sea level rise, which is another thing to notice for the graph. It's informative because of this. A little melt of ice, look how much sea level has risen, right? A little melt of ice will increase the sea level quite a bit. So be careful with the quantities. Sometimes it's called the butterfly effect. You've heard that expression of the butterfly effect. Butterfly effect, to dramatize it, they say the beatings of a butterfly in equatorial Africa will affect global climate change 20 years later. The tiny effect is like, I can put it more realistically. A slight fraction of percentage of degree deviation of launching a rocket may make the rocket miss the target altogether when it's 1,000 miles away. Just a fraction of 1 degree off the actual launching strategy, right? Just a fraction of a degree off. It's going to be, when you project that thousands of miles away, miss the target. All right, that's the butterfly effect.
Is that similar with you said about the butterflies of what you're talking about, the actual biology tests?
Well, no, bees, apparently bees are very sensitive to the environment, and there seems to be a global loss of bees right now on Earth. It's been detected over several years. And one challenge of that is that the bees are great pollinizers. And they pollinize in agriculture. They're very needed because agriculture, the farmers count on the bees to pollinize their crops. You know, and bees are not around, then the crops don't get pollinized. So it's a problem. On that is on the pragmatic side, aside from the fact that the bees are being impacted negatively by climate change. Okay, so I talked about that slide already. We have a few videos here. And then I think after we see a few of these, we're going to take a break. Let's see, it's 10:20. Yeah. So after this, we'll be about halfway. Let's look at, they're all pretty short, as you can see. This is, hold on. Oh,
It's $79.
I have to optimize here. The people are not telling me what to do with the website. Optimize the Zoom. All right.
Is taking the world by storm. Don't buy another flashlight until you've seen what this new.
Thank you. All right.
In 1978, satellites began continuously observing the polar regions, and the dynamic beauty of the Arctic sea ice was revealed.
Okay, so 78, rounded up to 1980, so 40 years ago. And there's going to be a time-lapse photograph of satellite imaging over the years of the Arctic ice, right? Arctic ice, starting 40 years ago approximately. This is, just to place yourself, this is Greenland here, all right? And this is Northern Canada, the Northern Territories. Alaska would be all the way to the left over here.
What we expect to be a solid mass of ice is actually in constant motion. As researchers continue to seek a deeper understanding of this region, new information about how sea ice changes is coming to light.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, senior research scientist at the National Snow and Ice Data Center.
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice.
Remember, it's floating on the top.
Over the years, the ice pulses around and moves around towards the top along the coast of Greenland.
It flows out in the winter.
The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older. And particularly in the region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around oftentimes for several years and gradually getting older and thus getting thicker. Eventually, the ice will spin out of that gyre and go out through Fram Strait. In the past, we've always had enough ice growth and ice aging, enough ice surviving the summers to replenish the older ice that's lost. But in recent years, we've seen less replenishment. There's been more melt during the summer, so the ice that goes out through Fram Strait has not been compensated by the ice growth. In addition, especially in recent years, we've seen some pretty remarkable things in the Beaufort Sea, where that area that used to be a nursery for the development of the older ice allowed the young ice to age and mature. What we've seen instead is the ice is now more broken up, more scattered, and that's allowing the older ice to melt within the Beaufort Sea. So we're seeing the Beaufort Sea go from a nursery to a graveyard for older ice. As we get towards the more recent years, much of that oldest ice, the ice that's older than 5 years old in the bright white, has almost virtually disappeared from the Arctic Ocean. And the Arctic is now dominated by younger and thinner ice.
It's quite a contrast, no? We go back between these two, and that's less than 40 years, about 30. Okay. Now, again, 40 years in geologic time is very short time scale. Okay. So we'd have to see long term if this eventually gets replenished. But for now, it's losing ice. And that's all ice melt then contributes to the sea level rise. Not as much, though, not as much on the North Pole than the South Pole. Why is that?
Because of the sun and the moon, right?
Not necessarily. When you think of a glass of water, let's say you have a glass of water with an ice cube inside, you mark the edge of the glass where the level of the water is, all right, of the liquid water, you mark the edge, and you let the ice cube melt. Is that going to increase or decrease or stay the same, the level? How many say increase? How many decrease? Stay the same? Don't care. Doesn't matter. No, it actually stays the same. Stays the same level because when the ice cube is in there to begin with, it has already displaced its volume. It has displaced its volume, so the water is already at the volume that it's going to be. And when the cube melts, it will stay at the same level because that ice cube has already displaced its own volume. Okay, so that's why the North Pole, even if it were hypothetically to melt totally, should not significantly increase the sea level, except for Greenland, if it is a different story, because of the gravitational pull of the ice, the horizontal gravitational pull, which I'll show you in a minute. It's very interesting. In contrast to the South Pole, which is much larger than the North Pole, number one. Number two, it's a continent. So the ice that is on top of Antarctica is not floating on the Pacific Ocean. It's on top of land. So when that ice melts, that is a contribution to the sea level rise, all right? So that has much more impact. The melting of the South Pole has much more impact on sea level rise than the melting of the North Pole. It's different. Because this is basically an ice cube that is sitting, but not exactly, because it's also kind of anchored on the edges of the continents. And so it's not totally displacing its volume. You know, it's partially displacing its volume, but not totally. Okay, so that's one. Let's see. This one is on drilling, because I talked about the ice cores and how they're trying to get to the different layers vertically, and the challenges that are there.
An NET television production.
And this is Antarctica, South Pole.
Antarctica is the iciest place in the world. There's so much ice here that only a few valleys in all of Antarctica are virtually ice-free. Everywhere else, ice encases the continent. But Antarctica's icy cover is deceiving. Surprisingly, much of this ice is on the move. Antarctica may appear to have a single coating of ice, but not all the ice on the continent is the same. The majority exists as ice sheets that cover the land and slowly move towards the sea. From Land's End, the ice continues to move as ice shelves that extend over the sea. And beyond the ice shelves is seasonal ice that freezes the sea in winter and thaws in summer. Polar researchers use the 3 types of ice to detect how Antarctica affects global climate. 600 miles from McMurdo is the West Antarctic Ice Sheet Divide, the high point of one of the world's largest ice sheets.
We're a mile above sea level, and even though it's incredibly
1 mile
flat,
above sea
there's actually
level.
2 miles of ice below us. Most people think of this as just snow. My colleagues and I, this is a collection of chemicals and gases that are characteristic of the climate when the snow fell. Now, the snow here never melts, it just piles up layer after layer and gets finally compressed into ice. But in order to see those layers, you have to go underground. So let's check it out.
They're going to a hole. Yes.
It's a lot like looking at a very
Claustrophobic. So he said they are 1 mile above sea level. So there's 1 mile of ice there, okay, equivalent to a glacier. And then there's 2 miles of ice below sea level. So it's massive. And this is all compressed snow over millennia. As the snow compresses, it compacts into ice. Now it's underneath.
very high-resolution photograph of how climate has changed in the past. You can really see the different layers in the pit. So this is 1 year's worth of snow accumulation, and there's a second year's worth of snow accumulation here below it. And we can figure out what the climate was when that snow was deposited.
To the cores.
Researchers here are drilling cores of ice to investigate Antarctica's climate history. These ice cores contain bubbles of ancient atmosphere.
Real slow. Nice and slow.
Levels of greenhouse gases trapped inside the ice reveal times when conditions were cold or warm.
We're looking back about 100,000 years back in time, and that goes through the current warm period and the last glacial period.
But ice has existed here for millions of years. And since gravity steadily moves the ice sheet towards the sea, even the oldest ice can tell just part of Antarctica's climate past.
But the length of ice records only extends back to maybe 1 million years or so back in time. If you want to go further back in time than 1 million years, you have to go with rock records.
Finding the rock layers is a challenge on a continent covered by ice. As ice sheets grind across the land, they swallow up the rock layers that detail Antarctica's climate history.
There's been this erosional bulldozer, if you like, the ice sheet just bulldozing the rocks on the continent. There are no rocks left of the age we're after.
As an ice shelf extends over the sea, the warmer water slowly melts away the bottom of the ice, dropping stones to the sea bottom. So geologists are exploring places where ice has deposited them in layers of rock.
Those are called dry suits as opposed to wetsuits. The wetsuits are the ones that we use here, where water gets inside the suit, the neoprene rubber, and the body temperature warms up that water so that we maintain warmth within the wetsuit, right? But the wetsuit is wet inside, maintains the body temperature. Wow. Dry suits are sealed so that no water gets in, because if that water gets in, it's hypothermia. Right? Exactly. So these are called dry suits. They're thicker, more awkward, and so forth, and they're insulated. So the diver is actually insulated inside that suit. All right.
Best sites are the ocean basins beneath McMurdo Sound. Here, marine life thrives in the salty, freezing waters of the sea. Over time, different sea plants and animals have adapted to changing ocean temperatures.
Biodiversity.
Geologists with the Andrill Drilling Project will core into the seafloor rock layers to learn how long ice sheets have existed on Antarctica and how ice here has affected global climate.
Right now, Antarctica seems to be locked in a very cold climatic condition. That wasn't always that way.
Andrill geologists are not studying the ice itself. They're using sea ice, or the ice shelf, as a platform to support a rock coring drill rig. They're sending a drill through the ice and down nearly 1,000 feet of water to bore into seafloor rock layers. But drilling on ice is challenging. First, Andrill will drill on the McMurdo ice shelf. Although it looks like the ice is frozen in place, the ice shelf is in constant motion.
We're sitting on this floating body of ice, 600 feet thick. It goes up and down once a day with the tide, a meter or so. It's moving to my left at about 150 meters a year. One of the problems we have, if this ice freezes onto our drill string and it goes up and down with the tide, it's just going to rip it out of the ground all the time, and we won't be able to get any core.
So Andrill engineers created a hot water drill, a moving ring that shoots jets of steaming water to melt a wide hole through the length of the ice shelf. The hole allows Andrill to continue drilling as the ice shelf moves more than 70 feet during the 3-month drilling season.
And so what the drillers will do is deploy it on an angle and anchor it into the sea floor, and then the ice shelf will have moved over the top.
Then, Andrill will drill on thin sea ice.
We're standing right now in the southern part of McMurdo Sound. Seasonally, this region will break out. The sea ice that we're standing on will melt out.
Just 20 to 26 feet of sea ice supports Andrill's massive drill rig.
We have a drill rig that weighs 40 tons. That's before we add any drill pipe to it. So we add airbag flotation to compensate for the weight of the drill pipe that goes all the way to the sea floor, and we inflate that progressively as we add more pipe to it so that we can continue to drill effectively.
You know, the water is getting crystallized. You can see the water getting crystallized here, and that's how icebergs are formed. By the way, the icebergs typically are formed at the bottom of the ocean when water starts crystallizing and conglomerating into a mass of ice, and then when it's large enough, it will rise to the surface to float around, because ice itself, solid water, is basically water, which is less dense than seawater, so it floats.
Effectively.
Andrill's drilling innovations on sea ice and the ice shelf will reveal a continuous record of Antarctic climate conditions since the continent plunged into a deep freeze. To learn more about Andrill's climate research, watch these episodes of Antarctica's Climate Secrets.
Okay. So just the challenges that are there and the technology that they're using, it's fascinating, trying to get at the rocks underneath the ice layer to see what the geology was, the paleogeology and the paleoclimatology. Now let's go back to the northern hemisphere, here about Iceland and what I was telling you about first the melting of Greenland, which is basically the last huge glacier that we have on Earth. Interesting.
But Chucky, those drilling don't have any effect on.
Well, there's nothing out there, no? There's they are.
Yeah, I mean, going like that, and that provoke.
No, because it's very localized. Keep in mind when you put that, even that huge rig that they have and everything, you put it in the context of a whole continent. It's just a tiny little thing, all right? So it doesn't have that big impact. But they do have to account for the movement, the seasonal movement of ice horizontally, in and out, like that. Okay, now we're back on the north on Greenland, right? Which has this huge ice sheet on top of it, but that is also melting at an exponential rate, and you'll see the rivers
when most people
within Greenland.
Imagine the surface of the Greenland ice sheet, they picture a vast plain of blowing snow.
That's Greenland.
In fact, it is a very wet icescape, and it's covered with streams and rivers and gullies, all filled with rushing blue water.
Okay, and the ice itself, you see how it's grayish color, right? That's all dust and soot and dirt that has fallen on top. So that's also informative as it gets layered seasonally, because then in the winter, snow will fall and compress it in and will form those horizontal layers that can be studied for information of the past. But notice the actual rivers that are through Greenland on top of that huge glacier.
But the real shocker is that every single one of these rivers abruptly ends in a feature called a moulin, which can be a crack in the ice or a round circular portal in which all of the water flowing through the river penetrates down into the interior of the ice sheet. So what we've learned is that the Greenland ice sheet is not a featureless plain of ice. It's more like Swiss cheese, through which this meltwater is able to quickly and rapidly flow over the ice, enter into the ice, and then escape down at the downstream edge to flow to the global ocean. One of the most pressing environmental problems of the decades and centuries ahead is rising global sea level. And one of the leading causes of sea level rise is the melting of ice from glaciers and ice sheets. And Greenland in particular is the single largest melting chunk of ice in the world. We know from climate models and weather stations approximately how much melt is being formed on the surface of the ice sheet, but what we don't know is if that water is truly escaping the ice sheet to connect to the ocean and contribute to global sea level rise. So for the past 5 years, I and my dedicated students have been studying this problem using a combination of satellite remote sensing, using very high-resolution military-grade imaging systems, as well as intensive field work involving deployment of autonomous drifters and drones, tracking and studying one of the least understood hydrologic systems in the world. What our research shows is there is a clear and definite connection between climatological melting on the top of the ice sheet and the downstream outflow of water to sea level rise and floods in the rivers moving over the Greenland coast. There are two take-home messages from this research. The first is the discovery and a new appreciation for how significant these superglacial river networks are for quickly and efficiently removing meltwater off of the surface of the Greenland ice sheet and exporting it to the global ocean. The second is we now know that the fundamental assumption of these models, i.e. meltwater produced on the top contributes to sea level rise at the bottom, is in fact correct.
Okay, so that's one major conclusion, and that's Greenland. The other interesting thing about Greenland is that because it's such a large chunk of ice on top of this island in the North Atlantic Ocean, it impacts not only the coast of North America and like the Labrador and Canada, which is closest to Greenland, but also on the European side. And generally, the east coast of North America and the west coast of Europe, and Europe in general, are two of the largest, most densely populated areas in the world. Okay, and so sea level rise, I mean, it's all urbanized, basically the coast, the east coast of here, of the United States, and then over in Europe. So sea level rise will have an impact first on the coastline, right? So having said that, this is something that perhaps very few people are aware of, which is the actual, at least I can turn off the sound. The actual
Most men, 99% of them, are unaware of this traditional 16-second Japanese ritual that could shrink
gravity from the ice
near a melting ice sheet to
horizontally. All right, so this represents, it's a diagram of Greenland, and the ice itself is exerting gravity, and it's exerting gravity horizontally on the water, on the liquid water around it, the North Atlantic, toward itself. So it's keeping that level of sea higher than it would be without the ice. Again, the ice sheet on top of Greenland is so massive that it's actually exerting gravity horizontally, pulling water, liquid water toward itself. And so it's keeping the sea level higher in the North Atlantic than it would be without the ice sheet. So if the ice sheet goes, then this sea level is going to actually go low first, and then on the sides go back up. Anyway, watch this little video that
opposing
explains
effects influence local.
I turn off the sound. Let me start again. It's only a couple of minutes.
Near a melting ice sheet, two opposing effects influence local sea level. A weakening gravitational attraction lowers the sea near the ice sheet, while at the same time, water flowing into the ocean raises it. To take a concrete example, imagine that the Greenland ice sheet suddenly collapsed into the sea. Globally, the meltwater would raise sea level by an average of about 22 feet. But relatively nearby, in places like Scotland, Norway, and Newfoundland, the disappearance of the ice sheet's gravitational tug on ocean water would cause sea level to drop.
Right. Again, it's the gravitational pull of ice horizontally toward it, which is, we normally don't think in those terms because we think of gravity as the Earth pulling toward the center, right? But every massive object is actually exerting an attraction toward itself. It's just that these massive objects are very tiny compared to the gravity of the mass of the Earth. But ice is large enough, natural ice, like the ice sheet on top of Greenland, is large enough to have an effect on the sea around it in the North Atlantic. And it actually pulls in. So when that ice sheet collapses, then that sea level is going to change. It no longer has that horizontal gravitational pull. So it's kind of counterintuitive. So it's not just the melting of the ice into the ocean, but it's also the gravitational pull that ice sheet is exerting around it. around itself.
Father,
Yep.
two questions on Greenland.
Yep.
So is Greenland like Antarctica, that it has land and then an ice mass?
Exactly. So you can think of Greenland as an island. It's kind of a triangular island, right? But on top of it, it has a glacier that is about a mile thick. Hmm.
So that's an Arctic.
That's, yes.
In the world or in the north?
Well, in the north, because in the south, it would be the South Pole, it would be Antarctica. It's, maybe it's a technicality, but Antarctica technically is considered a continent, whereas Greenland is considered an island. So it's the largest island ice sheet there is. Greenland.
What are the forces that bring moisture to the poles?
Moisture,
Because it doesn't rain there.
well, it rains in the way of snow, but it does snow in the poles. It's not the Hadley cells, right? There's a third Hadley cell up there. There's the Arctic Hadley cell that goes around, picks up moisture from the 60-degree latitude and takes it up to the 90-degree, and then it falls as snow. And that's the deposition snow that the fellow was talking about, becomes ice. So it does snow in the wintertime. They depend on that snow for the buildup of ice that melts in the summer to replace it. That's the cycle. Yeah. So you can say snow, it rains in the way of snow in the two poles. Okay, anyway, now we're going to talk a little bit more about winterization and tropicalization, but it's almost 11 already. So why don't we take a little break here? All right, 10:50. Let's be back by 11. And then we'll continue. Okay. Oh, thank you. I had not. So let me pause. Pause recording. Resume recording. I have one last little video here on total ice melt. Let's see if this one works. These ads.
Are you recording something?
Yes, thank you. Recording. Maybe an ad here. Let's see. Oh, yes. So this one, I think really this one has no narrative, but basically what it does is projects the melting of the ice, total melt. So a full tropicalization, what we call tropicalization of Earth, which is the North Pole melts totally. So it becomes an Arctic Ocean, navigable, right? And then the South Pole also melts. So Antarctica is exposed, the rock, bedrock, and tropicalized. And Greenland, of course, and then the glaciers of the world, which are very tiny at this point. But those are the three major contributors of ocean water. And if that rises, to what level it would rise along the coast, and what coast would be disappearing. All right. So it goes around the Earth, looking at the coastlines that would be disappearing if we go to a full tropicalization, as has been before, at least 4 times in the past 500,000 years, with those cycles of winterization and tropicalization. So here we go. It's only about 3 minutes, so it's very fast. Notice it points the coastline cities that would be buried under, or would be drowned essentially. Would be flooded. Proper word. That was Europe. Going through Asia now. The very low-lying ground there, all the way to Beijing. South America, the whole Amazon basin. Yeah, very low-lying ground. Buenos Aires underground, underwater. I think it's going into North America now. Yeah. Okay, here we go. North America. That's the Sea of Cortez. There we go. West Coast. Of course, it's very mountainous there, but the East Coast is the biggest impact. There goes Florida. Get out your snorkel. See how far in it'll go. Dramatic. Cuba is broken up into little islands. Sorry, you had a question? Or?
Do you think that the Bahamas would disappear?
Well, yes. See, it's all low-lying ground. Low-lying. So a lot of the islands, what is generally the Lesser Antilles and the lower islands will be underground. And this has happened before. That's why we're standing on top of crushed coral. You know, how did this coral get here? It wasn't truckloads from the ocean from the shore that brought it here. This used to be a whole coral reef, the whole peninsula. And there it is underwater. So that's the amount of water that is being held, mostly in the poles and then Greenland. Those are the three major deposits. Okay.
How long does it take?
Well, anybody's guess. And like Jose asked earlier, you know, it's hard to. We're in an interglacial period right now, in between, and it's anybody's guess which way we're heading. Because in addition to the CO2, which is being produced, let's say artificially out of the system, remember the carbon budget that we did? The annual carbon budget was in excess of, I think it was 4 gigatons per year that was accumulating of CO2 that was not being absorbed by photosynthesis. There are these geological processes that are going on in the background, right? Like the precession and so forth, and volcanic activity, etc., which are out of our control. So any one of those could also be addressed. And that's just within the system. What if at some point we get impacted by a meteorite? Just a couple of weeks ago, there was a report. Remember how NASA sent a rocket to impact an asteroid to see if it could deviate it from course, and it did. Now, they didn't tell us how much it was deviated from the course, right? But that was a test. That was a test. They sent a rocket to impact the meteorite to see if they can move it, or an asteroid to see if it can.
And there was a planet that was impacted by a meteor.
No, it was, oh yes, and a meteorite hit a planet, right? And then we also sent us another probe into the moon to do something else. So there's a lot of research going on there. I guess some of the stuff that they're seeing is classified and they don't tell us. I don't know, but at some point it could be. We've had at least one evidence already about 65 million years ago, and seemingly this huge meteorite is buried several miles into the crust of the earth down in the Yucatan Peninsula, and it's buried down there. That was the one that impacted 65 million years ago, caused such a huge dust storm and ash and from the burning and everything else that it covered the earth and killed the plants first, then killed the animals that lived on the plants, and killed the animals that lived on the animals, etc., etc. And the end result was wiping out the dinosaurs. Okay, I want to take a little shift now. Well, just to go over this tropicalization thing. Basically, it would be, for example, Alaska turning into a tropical rainforest, right? And we actually have some evidence of that. Not that it's happening, but it has happened in the past. And what is the evidence that we have that Alaska, for example, and the whole northern territories of Canada were tropicalized at one point, that had lush tropical rainforest growing there? Fossil is one, right? Like the Burgess field in Canada, but also fossil fuels. In other words, petroleum. There's oil in Alaska, there's oil in northern Canada, right? Petroleum comes from rotten forest. So obviously there were tropical rainforests up there in abundance at some point, and then over geologic time, those got buried and became fossil fuels, not only petroleum, but also coal and then natural gas, right? So we have evidence that this has happened before in geologic time. And that's what we call a tropicalized Earth. So it wouldn't be the first time that the sea level rises so dramatically. All right, now on the oceans itself, since we're talking about sea level, another impact of CO2 is as it mixes into the water, it forms a carbonic acid. It acidifies the earth, the ocean, all right? And so by acidifying the ocean, it changes the pH. The pH of the ocean is a little bit on the alkaline side. So there's a little scale here. 7 is neutral pH, right? But the pH scale, as you know, is a logarithm. Again, it's a logarithm because the scale itself is from 0 to 4 to 14. So 7 is middle, neutral. Less than 7 is acid. Greater than 7 is alkaline or basic. But it's an exponent. It's an exponential. What I'm trying to say by all this is that a small change in the pH is a large change in the acidity or alkalinity of the substance, right? So for example, a change from pH 6 to 7, or if we go rather, let's go down from 7 that is neutral to 6, pH 6, that means that that water is 10 times more acidic just from pH 7 to 6. It's a factor of 10. Right. So small change in pH again has a large impact on the acidity or alkalinity of the water. And it's estimated that the average pH of the ocean was 8.2 before 1850, going back about 100 years, more or less, a little less, less than 100 years, 8.2. Now it's at 8.1. So it's going toward acidification, right? And that's mostly due to the carbonic acid. Carbonic acid is a mixture of CO2 when it mixes into the water. So if we add acid to an alkaline substance, first we neutralize it, and then eventually if we continue to add acid, then it acidifies that substance. The general impact is a negative impact because it stresses the system. And one of the things that is stressed the most is coral and the whole coral communities, because coral are a base. You can think of corals like condominium. Many other creatures live around the coral, on the coral, in the coral, right? And so it's the basis, it's kind of the sea basis for a lot of biodiversity, especially in the tropical and subtropical regions of the world, where corals are most abundant. So it causes something that's called coral bleaching, which doesn't necessarily kill the coral at first, but eventually it does. And that's because coral is a symbiotic relationship with little microorganisms that live inside, all right? So let's see, first, just coral by itself. Yeah, so these are corals of different colors. And what they have is inside, so coral itself, hard coral, because there's also soft coral that is not calcium base is rather protein based, so they're soft and they move around. They're also known as alcinarians or other names. But hard coral, the skeleton is made of calcium carbonate. Calcium carbonate is kind of a mineral, and it is hard, and it gives them their structure. That calcium carbonate is white. It's white in color. And the polyps of the coral themselves, the polyps are typically transparent. The actual animal, each individual polyp is transparent. But then they have little microorganisms that live inside the polyp. Okay, and they're called zooxanthellae, coral and zooxanthellae relationship. And it's a symbiotic relationship, right? These little guys, you see them? So here's the polyp of the coral itself, which is transparent, but then it gets these little creatures inside. Some are can photosynthesize, and that's what they have different colors, and they provide nutrition to the coral. The coral itself provides a protected, stable environment, internal environment where they can live, okay, instead of just floating around. And so that's typically what gives the color to the coral. When coral is stressed, either with too high temperature or too much acidity, then they expel the zooxanthellae. They get upset and they take it on their symbiotes and they expel them. They shoot them out. Right? And so, and that's why they look. It's called coral bleaching, because then, since the polyp itself is transparent, what we're looking at is the skeleton, which is white, kind of similar to bone. To looking at a skeleton of a human, it's going to be white, right? Because they expel the zooxanthellae because they got stressed. The coral got stressed, and it gets stressed either because of high heat or acidity or change in the pH, basically. Then what happens when they expel the zooxanthellae? Sometimes they cannot get enough food for themselves, so they eventually end up starving to death. And then the polyp itself dies, and you have just the bleached coral left. But at first it was puzzling because some patches of coral went white, bleached, and people assumed that they were dead, and then they came back because the stress changed. The stressor was taken out. Temperatures went back to normal, for example, or the acidification was replaced by clean water, and then the coral regenerated. So it wasn't really dead. It was just that they had lost their zooxanthellae, but the polyp was still alive. It was just transparent. But when the polyp dies, then that bleaching is not coming back to life, right? So that's what it's called, coral bleaching. And when the coral actually dies, many other microorganisms and other organisms that depend on the coral will also die. For example, the parrotfish that literally eats the coral and then poops out the sand, right? Those fish will also be without a food source. So it impacts a whole ecosystem. Okay, that's with regards to ocean acidification with the increase of CO2. Oh, yeah, here's an example of a thriving coral community. As you can see, very biodiverse. By the way, most of what we see on the ocean floor, typically it's animals. It's not plants, all right? Now, there are algae there and other phytoplankton and microorganisms that can be plants or plant-like, but most of what we see is actually animals, including the corals and the sea anemones and all that. Even though they're sedentary, they're benthic, they're fixed onto the bottom of the ocean itself. So when it bleaches, it goes this way. And once the polyp dies, then this structure will be bleached for life, and it will be eventually eroded away and become part of the sand. All this to say then that monitoring coral throughout the world, especially on a strip that is more or less in the tropical and subtropical regions of the world going around the globe, monitoring the health of coral gives a good estimate of the health of the water quality itself that is irrigating that area of the earth. Okay, I want to continue on the track then on biodiversity, the whole issue of biodiversity, which is the number of species, both plants, animals, fungi, bacteria that can live in a particular region, right? In general, what's your intuition? Where is the most biodiversity on Earth, whether it's land or ocean? Near the poles or near the tropics or in the mid-regions? Near the tropics. So generally warmer weather has greater biodiversity. It's able to maintain more variety of metabolisms, if you want to put it that way, for variety of species, okay, generally. So as the weather gets colder towards the poles, then fewer organisms are able to survive. Typically, for example, fewer insects and invertebrates in general tolerate cold weather. Also reptiles and so forth. But generally, the tropical and subtropical regions are the ones that have the largest biodiversity, not only of plants, but also animals and so forth. So that is monitored. And this is a little lesson here on biodiversity. Take out the sound first for a moment. This goes on. Something about lipstick, I guess. Okay. So as a professor, he's just explaining a little bit what this biodiversity is like and how it's impacted by a number of factors, human and non-human factors.
Hi, it's Mr. Anderson, and this is AP Environmental Sciences Video 30.
Yeah, the professor talks a little fast. Okay, I haven't figured out a way to slow this down, but he has some graphics that are pretty informative. So try to follow the graphics if you can. Here we go.
35, it's on the loss of biodiversity. Way up in northern Norway is the Svalbard Peninsula, and on there scientists built a giant seed vault. It's protecting the seeds of humanity, our crop seeds, into the future. They chose to put it there because it's protected against tectonic activities. It's really, really cold. And also as the sea levels rise, it's going to be protected as well. The idea was hundreds or thousands of years into the future, we could go there and grab seeds and then start growing those crops again. Unfortunately, we've already had to make withdrawals from that area. And the reason why is the war in Syria put a lot of these drought-resistant crops at risk, and so they've had to take more seeds out and they've moved those to Lebanon. But it does kind of get at this idea of the importance of biodiversity. Biodiversity is not only species diversity, but it can be genes, species, especially our domesticated crops and livestock, and then ecosystems themselves. And they have value. They give us our resources, and they also do these ecosystem services. And they're at risk. We're seeing biodiversity loss all around the planet. The causes are habitat loss, invasive species, climate change. We also have overharvesting, and then finally pollution are all impacting biodiversity. And so it's led to conservation. What do we do first? We have to figure out where that biodiversity is being lost. We have to figure out the conservation status of these organisms or areas. And then finally, we can pass laws and treaties to try to preserve a lot of that biodiversity. And so again, why do we need biodiversity? It's where we get our food. It's how we filter our water, energy, medicine. We all get that from our environment. And again, our environment also does these ecosystem services. They keep our climate stable. They decompose material once it's died. They pollinate our crops. And so we need biodiversity on our planet for resources and to do these services. If we define what it is, it's simply a variety. Variety at the genetic level, at the species level, and at the ecosystems. And so those genes that organisms have, once the organism is gone or the gene is gone, it's gone forever. It's extinct. Species as well. These are all the fruits found in a certain area of the tropical rainforest, but also we're talking about the crops that we have. And so I think it used to be we had around 8,000 different types of apples that were being grown, and now it's 100. And if you look in your own supermarket, it's way less than that. And then it's ecosystem changes as well. Once an ecosystem is gone, coral reefs, for example, you can't build that back again. And so what is causing this biodiversity loss? Well, when I was trying to come up with a quick way for you to remember these 5 things, I came up with this mnemonic. And so if you think of the biodiversity COP, and if you think of high COP as a way to remember it, if we put those in order, habitat loss is the first big impact on biodiversity. So deforestation, when we're cutting down those rainforests and planting crops. Right here we're growing soybeans. This is looking from above, where we used to have a tropical rainforest. We're reducing that diversity and we're replacing it with one simple crop. Invasive species, this is kudzu. It's a plant that was brought from Asia. These are the zebra mussels in the Great Lakes that they're really wreaking havoc. They came from the Mediterranean. We're also seeing climate change impacting biodiversity. So if we look at the polar bear, for example, will they go extinct? It's hard to tell. But if we look at all the areas where they used to do well, we're seeing a decrease in the optimal polar bear habitat. Also, over harvesting. Humans have been harvesting animals for a long period of time. The dodo is extinct because we killed all of the dodos. And we're also seeing over harvesting now, especially in our aquatic systems. And then we can have pollution. Pollution's impacting the environment as well. So if we look at that Deepwater Horizon explosion, that led to an oil spill, which is impacting biodiversity in the Gulf of Mexico. And it'll take us years to figure out how that impacts it. Now, this has been going on for a long period of time. Extinctions are a part of nature. And if we look back through the fossil record, we've seen 5 major mass extinctions over time, and they have different causes.
Sorry, yeah, okay, so this is a little very synthetic. There are the mass extinctions that have occurred, and then after that, also there's expansive radiation, but basically these are the geologic eras, like for example, Triassic, Jurassic, Cretaceous, right? And this is the Neolithic, which is our current geological time.
But most scientists are pointing to right now as the 6th mass extinction. This is mass extinction caused by humans. We're seeing extinction rates that we've never seen before, biodiversity loss that we've never seen before, and its cause is us. And so how do we solve this problem? Well, the first step is to identify where the problem is. And so the IUCN, International Union for the Conservation of Nature, has been around for over a half a century, and what they've done is come up with these different statuses. Extinct in the wild would be one where we maybe have them in a zoo, but they don't exist in the wild. Then we have critically endangered, endangered, and vulnerable. Then we have near threatened, and finally areas of least concern. And so if you go on Wikipedia, you can look up any animal or any plant, and it's going to tell you its conservation status. So for example, the whooping crane are endangered. The California condor is critically endangered. Humans, you can imagine, are an area of least concern. They've then created this red list where we look at how many of these species fall into these threatened or these red categories. If we look at mammals, almost 20% or over 20% are in this threatened kind of an area, and amphibians are really at risk. And so what do? Well, what we can do is pass laws. So in the US, we passed the Endangered Species Act in 1973 to protect species and the ecosystems on which they depend. And so it essentially is a list. So bald eagles are a classic example that were added to the endangered species list. And so there, I think, were around 500 breeding pairs in the lower 48, and now there's over 10,000. So once they recover, we remove them from that list. Grizzly bears were added. Their population is coming back. In Montana, there's a big debate right now over do we remove them from the list or not? But it also has to be balanced with human resources as well. So logging, for example, can impact certain species that are going to be found on the endangered species list. We've also seen global changes. The Convention on Biological Diversity in 1992, all of the green countries here signed on that biodiversity is important, it has an economic import, and that we're going to try to protect it. But again, it's not legally binding, and so we're still seeing huge decreases in biodiversity. And it goes back to the first thing I talked about in this class, the idea that the planet supports society, but society is driven by economics. And so we're never going to see decreases in biodiversity loss until there's an economic incentive or a way to do that. And so did you learn the following? Could you pause the video at this point? and fill in the blanks? Well, let me do that for you. Biodiversity has value. It's a variety in the genes, species, and ecosystems, again, especially the domestic ones that we need to survive. That loss is caused by high COP, so that's habitat loss, invasive species, climate change, overharvesting, and pollution. And then how do we solve this? Through conservation, we figure out the status of those organisms or maybe those ecosystems, and then we start to protect them through laws and treaties. So that's it, and it's also the last of the videos on AP Environmental Sciences, so I hope that was helpful.
Fast talker, but he puts it all together, right? And I think it's realistic also to bring in the economic factor, because within the market economy, we have to make it work somehow, right? We can't just pull the plug all of a sudden overnight and expect industry to continue our same lifestyle that we have before the plug was pulled. So we have to figure out a way within the market economy, how can this be done?
How are you gonna move all the people out of those places?
Well, yeah, that's another very complicated issue, right?
Father, just based on
Mhm.
if it, you said economy, that there's a lot of different economies.
Yes, yeah.
So if the economy is what is a value for human existence, as opposed to what is a material and measurable value of money,
Right.
then it's an easier equation to
Uh-huh.
relate the biodiversity to human. And what struck me in that
Yes.
past video
Right.
was when there was a classification of species,
Yes,
and then he puts humans as the species of least
least
concern.
concern.
And that's right. So once you do that, then this approach is not going to be
Right.
practical. Because
Right.
we're the creature of most concern.
Exactly. It's skewed. That's looking at it, let's say,
Right.
biologically as the human as one of the 2 million species that we've classified, and approximately 10 to 20 million that are still out there unclassified, right? So, but it is skewed in the sense that it puts us kind of in a natural setting, but we're not in a natural setting right here, right now. And here, we're not in a natural setting. We're in a very artificial setting. So how to put that added issue of technology, artificiality, and still keep the human on planet Earth. But yes, we're in our category of our own. We're in a very unique category
Right.
in that sense.
Yeah, and I'm just kind of relating it overall to the value of human life.
Exactly. And how to,
Get into the logical
yes,
divine creation.
exactly.
We're unique.
Mhm.
And so the world was made for our Lord,
Mhm.
created by our God.
Yes.
For Christ and for us to live and share in His love. So we are actually given the world. Right? So we don't live in an I see we live in an artificial world. We live in a world that we're created to live. So
Yes.
we are created to have housing, to have
Exactly.
electricity, and to
Yes.
work with nature and the gifts it gives us.
Uh-huh.
So if I'm seeing a bald eagle,
Right.
the paradigm is really, why is that bald eagle a gift to me as opposed to an expense?
Mm-hmm.
Because
Yeah.
I believe I heard a story that the most abundant creature on Earth is the ant.
Really?
So
The ant family also,
Yeah,
many
yeah.
different species of ants, right? Most abundant by the numbers, by the numbers.
So if you look at
Yeah.
it from that perspective, the ants are overwhelming the Earth. They're over
Yeah.
I would say consuming.
Right.
Because they're far more ants numerically than for us.
Mhm.
Yet I bug spray and I kill all the ants in my kitchen.
Right.
No issue. with
No
that.
compunction about killing ants in
Exactly.
the kitchen, yes.
So in my kitchen, that ant is not a value, but
Mhm.
maybe out in the wild, they
They
are
serve some
obviously
function,
from
right?
their-
They're part of the
obviously
ecosystem, part of the balance. Oh, yeah, oh, nice.
So that's what kind of I'm getting at. I think if you give it like monetary values, say like an eagle is worth $20, and so you should try to save an eagle, so you save $20, or I'm gonna take away $20 from you every time you kill an eagle. I think that cheapens really the value of the whole.
It's too simple. We can
consistency of what we're trying to.
Yes. Yes. I think one of the challenges is that we don't all have the same philosophical or theological constructs, right? Because I could say, why should the bald eagle continue to exist, for example? You know, why should the bald eagle exist at all? You know, why can't I kill all the bald eagles that there are? It's a stupid question, of course. But why is it a stupid question? You know, why should any species exist at all? Why can't we just be the species? All we need is a benevolent environment. In other words, where there's oxygen and water for us to live, and then everything else will be artificial or synthetic.
But in the same, I mean, it's not the less concerning in the sense that there's, I mean, going back to completely. This is very important, and I think it's a stupid question to ask why these other species are necessary, because yes, I understand of the balance and all that. In the other hand, there's a lot of injustice in many areas of the world where not even biodiversity can solve the real problem, like India or Africa, or let's go back to
they're human problems, right?
Yeah.
Human problems. They're massive. Right.
Cuba, you know?
Right.
Which it's very concerning. That's what I'm saying. So yeah, it's not
correct.
Yeah.
We also need to parse out the questions, you know, so that we can talk about them somewhat logically, because if we throw everything into the blender and then push the button, we just get mush. Okay. And so all the issues cannot be solved at the same time or even talked about at the same time. But biodiversity, at least, is one issue. There's one particular aspect of his presentation that a lot of people just take for granted, and I believe that he takes for granted also and moves forward, which is value. You know, it says that biodiversity has value, that species have value in themselves. And then he tries to justify it a little bit in a kind of a pragmatic way, because he says, well, it has value because they are of service, right? They filter the air, they filter the water, and one way or another, our food and our medicine and everything comes from there. But it doesn't have to be. In other words, we have progressed to such an artificial state that we can even grow now synthetic food and synthetic medicines, and we can clean the water. I understand that the water of New York City, for example, is cycled 6 times before it's finally sent out to the ocean. You know, anecdotally, I don't have a reference for that. But in other words, we have gotten so sophisticated with our technology that in one sense, we're dependent less and less directly from nature, right? I mean, when was the last time you plucked a chicken to eat it, to cook it? I've never plucked a chicken in my life, and I eat chicken all the time. Someone else has plucked it for me. Maybe it's a machine that does it. I don't even know who plucked the chicken, but somebody did, because I'm not eating feathers. I know that. You see? And so, in fact, talk about the chicken. I remember one time hearing about, I think it was in Israel, that they genetically engineered chicken to have no feathers. So they don't have to be plucked. But of course, they have to be kept indoors, otherwise they fry on their own alive from the sun, right? So, but that's something that's the level of artificiality, let's say, that we have been able to generate. In itself, I'd say it's neutral. It's neither good nor bad. It's all how we use it, right? It's like nuclear power. In itself, it's neutral. It's how we use it. But this issue of perhaps there's a natural intuition that biodiversity is of value. Now, for people of belief, I say that it's a reflection of God's creation, you know, and they have a certain right to exist as we do. Of course, when it comes for choosing between them or us, them being the rest of nature, I think we have to draw a line somewhere. In other words, we have to live somewhere also physically, right? And that's where I want to get into toward the end here with regards to human population and human population growth and the rate of growth. Because in my opinion, it's not necessarily following God's plan, is that population growth, all right? In other words, there's a lot of irresponsibility there, in my opinion, with regards to human population growth. That is not necessarily God's plan, but we'll get there, we'll get there. So with regards to biodiversity, the interesting thing about biodiversity is that climate change may impact it, but it's not as much as habitat loss. Habitat loss is the biggest thing of that impacts biodiversity, right? In other words, literally, physically, a place in which to live. And I keep using the campus, our own St. Thomas University campus, as an example, because to me, it's an example that we're familiar with. I've mentioned before that the campus is about 5 blocks by 5 blocks, more or less, kind of a square. It's about 140 acres. And the forest that we have here, the native / pine forest that we're trying to preserve, it's about 15 acres. So that's roughly about 10%, right? If it were 14 acres out of 140, that's 10%. So it's roughly 10%, means that the other 90% of the campus has already been developed. But this campus started about 60 years ago, precisely 1961. So in 60 years, and before 1960s, right, the whole campus, the whole 140 acres was undeveloped, meaning that the whole campus was a / pine forest. And even beyond the campus into Miami Gardens and all this, we go back 100 years, and the whole Miami Gardens and the whole South Florida was essentially a / pine forest. Okay, so just to use our campus again as an example, in 60 years, 90% was already developed, and it's only 10% left. But within that forest, we've had tremendous amount of biodiversity of all kinds of plants and animals and bacteria and fungi that live there that don't live anywhere else on campus. Some of those creatures do wander out and scavenge around, like the raccoons. They get into the trash cans and all that, but most of them stay in the forest. And you see just butterflies, for example, that are very obvious to see in the bright colors. You see them flying around all over the place in the forest, and you don't see them anywhere else on campus generally. So they're there. That's the little niche. That's all they have, is this little tiny spot of 15 acres within the whole, because you go beyond the walls of the university or beyond the fence, and you have essentially a residential area, and it's also commercial. There's an airport 2 blocks away, et cetera, et cetera. So it's totally all urbanized for miles and miles and miles around. So it's like a little island, right, of what we call an urban forest. Within that island, there's a tremendous amount of biodiversity that doesn't exist elsewhere around the place. That's all they have left. So an effort for preserving it, because it has that intrinsic value, it has value in itself. In fact, this Pope is making a lot of that argument in particular. That's one of the reasons why he chose the name of Francis, precisely inspired by St. Francis, who traditionally has been known as a lover of nature. So anyway, what I want to point out about all that is that with regards to biodiversity, the biggest urgency, if you will, or the biggest impact on biodiversity is loss of habitat, even more than climate change. As dramatic as climate change can be, loss of habitat, in other words, urbanization of the one species on Earth, because the other species somehow manage to interact with each other and establish their own territories and fit within the ecosystem. So here's a graph. I'm going to skip this news thing for the sake of time. You can see it later. But here are 2 graphs that show a very tight association and possibly even a correlation if we do some stats on it. The purple is human population growth. And when we project it out to 200 years, okay, 1800s to today, we see the curvature, the geometric growth, logarithmic growth, and extinction rates, which notice the first half of the curve is fairly flat. That is what we call the lag phase. And this, there has always been extinction going on Earth, but there's like a background extinction rate, okay? Just like there's a background mutation rate, for example, of the genes, of the DNA, there's always been a background extinction rate. Some species are disappearing all the time, forever, and new species are arising. That's what we call natural selection, evolution. But all of a sudden, or fairly drastic, around the 1950s, that curve starts to slope exponentially, all right? And it associates with the growth in human population. And so this is because these people are physically living somewhere, right? So they're taking up space that used to be natural space for other species. And so there is the association that is a very tight fit between extinction rates and human population growth. Going a little bit further into it, this is a map put together also by NASA, which has human population. We're going to get into this video in a minute, but basically what I want to point out here is what they call the Human Influence Index or human impact, right? From low to high, low green, high brown, reddish. You can see on this global map, again, this is a nice map to point out the land masses in the Northern Hemisphere. This horizontal line in the middle obviously is marking the equator, right? And this is what I was trying to say earlier, that most of the land masses are in the Northern Hemisphere. Okay. And so there's more ocean in the Southern Hemisphere. But look at the areas here globally. I would say globally, there are like two sets of 4 regions. I would say 4 regions of high impact or high influence on Earth, on the landmass, and then 2 regions of moderate impact. But major impact, we have basically the eastern half of North America, mostly the US, because Canada, we know Canada is actually underpopulated. This is called the Northern Territories of Canada, and it's all permafrost up there, so there's very little human population in that area, right? Some of it is taiga, in other words, forest of coniferous trees, of pine trees, but then you get into the tundra region where with the permafrost, trees cannot take roots, so there are no trees. Same with Siberia, equivalent cold, harsh conditions. But so back to the areas of human impact, the greatest major human impact, basically the eastern half of the US, Europe, especially Western Europe, then India in general, and East Asia here, including China, Korea, and Japan. And then moderate impact, in general, Mesoamerica, which would include the Caribbean, Mexico, Central America, and the northern tip of South America, Mesoamerica, right, Middle America. The Amazon, south of the Amazon basin here, equatorial Africa, and then Eastern Europe and into Central Asia, moderate in general, all right, including the Middle East. So we have these, I would say 8 regions total, 4 of major and 4 of moderate, which correlate to higher density of human population. So this little video that I found is one that traces the history of humanity by little yellow dots, okay? And the growth in population, and periodically it will show like an empire in historical time, okay? And it's only 6 minutes, so it moves rather fast, but the basic idea is that you see the gradual increase in yellow dots throughout the world. And each dot he'll say now in the narrative how much human population is in a dot, in a yellow dot.
An environment is a system.
A little low. Let me raise the volume. Okay, environment.
System of living things. The Earth is our environment. The capacity of our environment to provide space, to produce food, and to supply energy are all limited.
Right. So the space, remember, this is trying to get at that question. It's an open question of the carrying capacity, so a couple of things. First of all, planet Earth, which is benevolent to our living, etc. We are considered, for biological reasons, we are considered a single population. We're the only species that is considered a single population for all the 8 billion people that we are, right? Other species, remember, they form local populations according to the geographical region. Even if it's the same species, they can be different populations depending on where they're living. For example, the slash pine, which is the same species, Pinus elioti is the scientific name, slash pine. This population, this northern population of the county, looks physically different from the one that is down in the southern part of the county, Paride and South Dade area, that is called rockland pine, because that one is growing on top of limestone, and the limestone doesn't allow the root system to get large, so it stays on the surface. So those pines, they grow tall and thin and spindly like that, right? They don't get massive like these guys do with the big, thick trunks, all right? So they physically look different, even though they're the same species. So those are definitely two populations of the same species living in different local conditions, different environmental conditions. So it makes them look physically different, even though it's the same species. If you forward that over centuries and millennia, at some point, the pollen of one population is not going to recognize the eggs of the other population because there has been enough diversity, variation going on, and they may eventually evolve through speciation into separate species. Maybe the same genus, but there will be different species at that point that they cannot cross-fertilize. All right, that's because of geographical isolation, and that's the standard for speciation. For us, different in that we have the capacity to do what throughout the whole world? To move, to fly. So in principle, at least theoretically, a Chinese person can mate with a South American person and have fertile children, right? And so, which is the definition of a species. So we're considered a single population throughout the whole Earth as humans. And then the question arises, what is the carrying capacity for the human on Earth? When does the curve level off, right? Limited resources.
Limited. Humans thrive on less than 17% of the Earth's surface, and only about 4% will grow crops. We depend on these limited resources for our survival, yet we are increasing our population as if they were infinite. This fact is at the core of our environmental problems. On this map, we'll show population growth from the year 1 CE to the present and project our growth into the year 2050. Population concentrations will be indicated by dots, each of which will represent 1 million people. In areas where people are spread out and don't live in concentrations of 1 million, dots are placed in the middle of their approximate range. Historical references will be provided by images and text at the bottom of the screen.
Okay, now it's gonna run it. The heartbeat is a little annoying, so now there's no more narrative. But predictably, the heartbeat will increase. As you see, the yellow dots also look at the lower left clock running and ticking 1 year at a time, very fast, like a year per second. Because it's got to cover 2,000 years. So the higher concentrations begin in India and then Southeast Asia. Early little elsewhere, but every now and then there'll be a new little dot. These are the Mesoamerican empires beginning to grow. We're in the lower Middle Ages there. Europe is slowly getting more and more populated. Coming up to close to the year 1000, not yet. So predictably, the areas that started with high population rate, high population density will continue to grow that way, but new areas will start getting populated. We crossed already halfway, it was the year 1000. Now Western Europe is starting to grow faster. Mesoamerica also. This region, I don't know if you noticed, but this region underpopulated. So that points to high mortality rate, probably infant mortality rate, right? Because it depopulated for a while and now it's repopulating. Those could have been plagues. It's hard to tell. In general, the American continent is still very low population rate in 1700s. After the 1800s, it's going to start picking up. And New England area. Less than 100 years ago. Now, see the exponential growth? Less than 100 years, 50 years. Very good. It's incredible. The past 50 years, we exited that too fast. In the past 50 years, the humongous accelerator, that's the logarithm, that's the doubling of the population rate. And anyway, well, let's watch the rest of the video here and let it run through.
Our population is expected to grow to 10 billion by the end of this century. Yet the Earth's size remains the same. Slowing human population growth and lowering our use of natural resources are key to reducing the impact we have on the planet. Through the decisions we make about our lifestyles, our numbers, and our consumption, we can all help preserve the health and beauty of our home.
Okay, it's interesting that he ends by referencing the earth as our home, which is also a phrase that Pope Francis used in his encyclical on 2015 on care for our common home, Laudato Si, right? It's the first encyclical, by the way, of the Catholic Church devoted to the environment. But so this issue of population growth and population growth rate, human, has been controversial for quite some time now. The point I tried to make last time was that it's mostly urban areas. Of course, those yellow dots are actually disproportionate, right? When we look at a map, the yellow dot is not to scale, because if we were to scale for 1 million people, it would have to be a much smaller dot. But it's impressive to see those areas of the world fill up with population.
So there was a significant exponential growth
Yes,
during the past 50 years.
50 years more or less, half century.
But now we're gonna get to 10 million at the end of this century. So that's
Right.
another 70, 80 years.
Exactly.
So there's now.
There seems to be a slowing globally, right? A slowing down. Exactly. There are a number of factors that play into that, but the biggest one, typically, of course, is contraception, right? So one way or another, it's not that people are pairing up less, couples are still pairing up, right? But they're just not having children.
So, yeah, you mentioned that it's been controversial because what we hear is that we cannot have children. Because if we continue growing, there's
Right.
gonna be enough.
Right, it will be overpopulated, right?
Exactly.
So we humans,
And this,
right,
so we also hear, we understand, or at least in my understanding, what we have done so far, is that that's not necessarily true because there's a lot of places of the world that we cannot, that we're not, humans are not there yet.
right. They're
And
not
that
inhabited
things
or
that-
high density.
Exactly, and everything about creation itself and the way humans are created. And again, about contraception and all that. It is more related to contraception than really just humans continue being able to have kids. I mean, that's what
Right,
we are.
it's a natural thing.
Right, but if we're not having children, really, we're not ending that by natural selection, but by human intervention, right?
Correct, correct.
So that is completely opposed to our bioethics in the way we, as a Catholic Church, as I'm just putting out our faith. The growing, it's not really the problem, I think, in the sense that we can continue to grow.
Right.
If we do it in areas that can be
Right.
providing resources.
Right, so this is where I see that the growing is a problem. Growing meaning the growing of the human population in an irresponsible way. In other words, if we go back to a seminal document, which is precisely on contraception, Humanae Vitae, but by Pope Paul VI, right? In the 60s, 1968, which was just a few years after the pill had come out. He talks about irresponsible parents. In other words, deciding between the couple how many children to have, when to have them, and so forth. But then the method to use, the method has to be justified also, right? For avoiding the children. So there is justification for avoiding the children or avoiding excess number of children. However, when we see that human population growth rate, a lot of it is, frankly, irresponsible behavior. A lot of men are just going around fertilizing a number of women and not being responsible fathers for any of those children. And the women are having a children. We see it in Latin America. We see it in general more in the Southern Hemisphere in general. We've seen it. I've lived in Latin America. We see it all over the place. We see it in Africa. We see it in Asia, India, right? And these people also generally have less access to contraception. And even if they do, it's not part of their culture in general. But what I see is that there's basically a lot of irresponsible behavior on both sides. On those who are avoiding children when they don't need to avoid them, and those who are not avoiding children when they need to, right? And so there's, in my opinion, there's a lot of irresponsible sexual activity going on in the human species. Irresponsible. In other words, the activity goes on without absorbing the consequences. And a lot of that is on the man. And then the woman gets saddled with all the kids that I've seen in Latin America, women with many children from several men, and none of the men are around to do the job as a father, So that's what I see, and that is a big reality of a lot of the countries down in Latin America, in Africa, in Asia, and in India, where those populations are increasing. In contrast to that, like almost to the other extreme, in the northwestern hemisphere of North America and Europe especially, we see a decrease in population, so that their populations are aging, right? Because fewer and fewer couples are actually having children. So it's such a contrast between the two extremes, and yet the same world is living those two extremes right now, the same planet. So I don't think that the argument is as simple as have all the children you want or not have any other children. You know, it's much more subtle and complicated than that, because it involves human relations, and one of the most complex of human relations, which is the relationship between a man and a woman. That's what I see. It's polygamy is another issue. You know, all these issues play into the mix. At the end, we have to deal with the numbers themselves as they are, and it is still increasing. But then one thing is to look at it globally. We don't have a homogeneous distribution by any stretch of the imagination. Again, in my opinion, a lot of it has to do with urban areas, large urban areas of high density. You know, the megalopolis that I talked about earlier. What do you think?
It's very complicated.
It is complicated.
I mean, I don't think it's about education, but that's not gonna happen fast, because as you said, and we have seen before here, especially here, I'm talking about North United States, we live in
the US.
Europe, it's a contraceptive culture.
It is, it's a mentality, right?
Children are not seen as a blessing.
Right. It's by exception. Having children is by exception, but the norm is to avoid the children.
You
It's
have a child,
kind of
oh
the
my God,
cultural.
this is a big problem, they have an abortion or not having it at all, so
Right.
let's take care of ourselves.
Right.
But in the other hand, in other places, and even here, I think, because what you said about irresponsibility, I think we all understand what sex consequences are seriously,
Right.
then people would act with more responsibility, but people, everything, music, TV shows, series, books, everything talks about having sex and having fun.
The culture is very, it's eroticized because also sex has been commercialized.
Absolutely.
And now it's used for selling cars, toothpaste. What does toothpaste has to do with sex in principle? You know, it's not, but everything has been eroticized to sell. It's been commercialized. It's part of the industry, it's part of the culture, and it filters in from childhood. We just grow into that kind of culture. The responsibility that would take to slow down human population growth, it's a huge responsibility. Most people don't own up to it. That's my opinion.
You use the word about urbanization,
Mm.
and I think a lot of this is driven by the urbanization of our societies.
Yes, right.
We're more agricultural. I think a lot of these issues wouldn't come to
Right.
the exponential.
Exactly.
type of
It's more
representation.
stable.
But I think the fundamental
Mm.
has to do with sloth and glut, because that's
Two
really
capital vices.
vice, which is really what supports society. When you say sloth, I mean, but we want things easy.
Right. Kind of a laziness.
Right? Yeah, I don't want to
Right.
actually have to sit down and
Do the work
and
and-
But and society feeds our
Yeah.
drive for
Gadgets are for that, right? To
Right.
make our life easier,
To make
supposedly.
I don't wanna walk, I'm gonna get in my car and drive, right?
Mhm.
It's just the nature of what we're giving into our nature.
Mhm.
And then from the gluttony perspective, I mean, obviously we have obesity with an issue and so on. But that's not what I'm getting at, that there's no satiety.
Right.
So, and I'll point to.
Open-ended, because appetites are kind of open-ended.
No, but,
Absolutely,
no,
and everything.
but they're
Including the sexual appetite is open-ended.
What do we think? When we say we're stalwarts in our society, we think of these new trillionaires, right?
Right.
It's like this, but why do you need to be a trillionaire? It's the same
Exactly.
thing with why is an eagle important? It's not. It is only because we make it important. And a trillionaire is not important only because we make it important. So we've lost that component of it, that there should be some boundary
The boundaries.
where you say, okay, this is enough.
Enough
It's
is
a good life, and why do I need to go get more?
Yeah, even
And
Paul,
so we overdo.
you remind me of a passage from St. Paul that mentions there's enough with the sufficiency, right? Why should I just continue to accumulate open-ended? And sometimes I've seen people who accumulate open-ended and they become more anxious because now they have more property, they need more cameras, more security, they have to pay more insurance for what they have. And then the stuff doesn't fit at home, so now I have to rent a storage space to put the extra stuff, and the life gets more complicated.
And then our nature as human being is to do that. So our gift is to be able to overcome our nature.
Right.
And
to
that's
set
what I think
boundaries.
we have to work on.
Yes.
To teach that somewhere.
Exactly, boundaries, how to establish boundaries and stick to them. Mhm.
But how could we?
Yeah, good habits or bad habits.
That really begins at home.
Yes, because it's the first learning, right? And as mammals, again, we can use biology because mammals tend to imitate. The progeny tends to imitate, and monkeys are particular for that, you know, but in general, mammals in general, they imitate their parents in what they do in the hunting process, scavenging, whatever they're gonna do to survive. So the parents teach the children how to survive. And for the human, it's no different. So the home environment is crucial for sure, which is another aspect that can be in crisis, right? Today in many places. But in general, I would say the home environment may be more in crisis in urban areas than in rural areas.
Right.
In general, I think the life in the countryside is healthier. Is more in contact with nature itself, with working the land and so forth.
Come to Alabama.
Exactly, you see?
We'll overpopulate Alabama.
Get ready for the urbanites of South Florida.
Government has to do a lot with this at some point.
It does. So we mentioned economy, then we mentioned politics, and it has politicized. I wanted to end on that note of the politicization of the issue, which is another reality. But before going there, with regards to biodiversity and conservation, going back about 100 years ago, the professor did mention this whole issue of conservation and laws and treaties. So the national park system, I wanted to put a little plug for the national park system in the United States because it has also been a model for many other countries of the world. All right. And it started a little over a century ago. It was actually enacted by Woodrow Wilson, who was president in 1916. All right. But the concept was started with Teddy Roosevelt in 1906. And here's Teddy Roosevelt on a photo. He was a hunter. Okay, he was a hunter. And so he was in tune with nature in that way and so forth. And he had the idea, the concept of establishing relatively large territories, tracts of land in the US that are a unique environment. So one of the conditions for a national park, right, as opposed to a state park or county park, is that it has to be a unique ecosystem that doesn't exist anywhere else in the United States. Right? It doesn't have to be necessarily a very large territory, but typically they are. And so Yellowstone is the flagship national park of the United States. And I had the privilege of going there one time with my brother and sister-in-law, did some camping. And it's essentially a huge caldera. It's the crater of a humongous volcano that exploded a long time ago. And now all that's left is kind of the basin. And that's why they get these fumes of hot air, of hot water steaming out, right? The geysers. And it's fascinating. So in a very cold environment in the winter, it's all full of snow. You have these hot springs of water in the middle of the snow, and the colors typically are different types of bacteria that grow there. These are extremophiles. Remember, we covered extremophiles are bacteria that love extreme conditions. It could be extreme sulfur, extreme heat, extreme salts, you name it. And some of these are polyextremophiles that tolerate several extreme conditions at the same time. So that's what generally gives the color, the different hues to all this water there. Anyway, that's the national park system. We here in South Florida are blessed to have two national parks. The Everglades, of course, is one ecosystem, but there's also Biscayne Bay National Park, which is out in the water. And it's totally marine. It's underwater, starting from the coastline. And so we're at the slice of Dade County. Basically, urbanization is between two national parks, the Everglades and the Biscayne Bay National Park, right? One is land, the other one is ocean. But not every state has a national park, for example, but many do. And we're privileged to have two down here in South Florida. Okay, so that was a great insight to preserve tracts of land in perpetuity and to establish actually a federal agency that takes care of those parks. So there's funding there as a line item for the annual budget in Congress, all right? And many countries of the world have imitated this system, used it. For example, Costa Rica is one that I know of. I think about maybe 50 to 20% of the geography of the land of Costa Rica is devoted to conservation, right? And so they've made an industry out of that, ecotourism. And because they have tropical rainforests, they have one of the highest biodiversities in the world there. And so a lot of people go just to observe nature, and they have gotten pretty sophisticated to the point that they have these hanging bridges, right, from trees to trees and so forth, and they have zip lines, and a lot of people go there to do ecotourism and camp and hike and all that. So they're making a profit out of it, and now it's world renowned to go to Costa Rica in Central America for the ecotourism. All right, so that's one aspect on the positive. Then a number of conventions. Here we have to go, I'm going to wrap it up with this because we're coming up to a COP27. I'll tell you what COP means in a minute, but this is at the level of the United Nations or global, some conferences that have gone on raising awareness for preserving the environment and so forth. So this is at the international, at the global level. So major environmental agreements and conferences started in the 60s. And one big one was in Sweden, Scandinavian countries, Norway, Sweden, what's the other one? Norway, Sweden, Denmark. They have always been very tuned with nature and so forth. The Norsemen were there, the Vikings and so forth, right? So they have large tracts of land for forest and also the fjords, beautiful coastline and so forth. Anyway, they were pioneers in this. They had a United Nations conference there, Economic and Social Council, bringing in the human factor in the 60s. And then in Stockholm was the famous Stockholm Conference in 1972, the Declaration on the human environment. In other words, trying to look at the human population within the context of the Earth, of the surface of the Earth, and the impact that we're having on the Earth. That was in the heydays of these conferences back in the 70s. And from there came the Stockholm Declaration, right, to preserve the environment basically as much as possible. I drew here, so it has been politicized from the very beginning. It's always been a political issue because you think of social, economic, And once you have economics, then politics is going to be involved in it too, right? And I draw here from a definition of Plato going back several centuries before the time of Christ. And so certainly way before we had all this population growth rate, that he defined the human as homo politicus. I find it interesting because the reference to politicus is in the original meaning of the word, right, of polis. So polis here is the root of politicus, and polis is the city in Greek or Latin back then. So polis is the city, right? So is the animal capable of living in the city? In other words, capable of urbanizing, supposedly, at a certain population density. But it turns out that this polis, when this human polis gets too dense, like in the megalopolis, we start getting major problems of infrastructure and crime and unhealthy living conditions and violence and so forth. So there's kind of a certain density beyond which we humans just become too aggressive. All right. So the ideal density for humans, I think we still have to work out what that ideal density is, but maybe kind of a suburban area where we have a little more land around us, right? Anyway, so Plato makes the point basically by his definition that we are in principle capable of getting along with each other and living in a civilized way, all right? But we still have to work it out. We have to work out all the politics of it and the economics of it, of how to live civilized without being at each other's throat. So therein lies the challenge, and the UN has taken up that challenge. You know, most of the nations of the world are members of the UN. About 194, I think, of 198 nations, practically every nation of the world participates in the UN. And there are a couple that are observers, like the Vatican, for example, is a permanent observer that doesn't have a vote, but can voice opinions. So in the 90s, a number of conferences started, driven by the United Nations on the environment and development. So they want to bring in the whole issue of sustainability, right? And one that had a lot of impact, it's kind of a watershed for these conferences, is the one in Rio de Janeiro in Brazil. And that was called the Earth Summit, right? It was in the news at the time, and it's used kind of as a reference point to start looking at the details of toxic chemicals, alternative energy sources, transportation, water, etc., all these issues that have an impact on human population. And so that was the Earth Summit in '92. And from there, they've been meeting every year, basically. The framework that came out of that was to try to stabilize greenhouse gases, right? So that it doesn't continue to increase and cause all the negative side effects that it has. And this whole issue of the anthropogenic mass extinction that we seem to be heading toward. Anthropogenic meaning generated by the human, in contrast with the other 5 that were just generated by nature's cycles on Earth, right? The mass extinctions that have been recorded there in the geologic record. In contrast to those, this one, anthropogenic, is being generated by the human species. So that's the one that we're trying to curb and avoid. All right, going from there forward, there has been, since '95, a conference on the environment at the UN every year since then, starting in '95. The first one was in Berlin, in Germany, and it was called COP. COP just stands for Conference of the Parties. So it's kind of cryptic. The acronym is cryptic, but it stands for Conference of the Parties. Now, what are the parties? The parties are the member states of the UN, those 194 states that I mentioned earlier, okay? So it's practically just about, it's like 99% of all the countries of the world are members of the UN with voting rights. And so those are the parties. So the Conference of the Parties is a yearly conference on the United Nations that addresses environmental, the impact of humans on the environment. And as you can see here, I've listed them in different parts of the world ever since, right? Now, fast forward to one that was high impact, was the, you've heard about the Paris Accord and Paris Agreement. That was in 2015. It's amazing that that's been 7 years already since the Paris Accord, all right? Symbolically, that's the one that President Trump pulled out of because it was not to the economic advantage of the United States, in the sense that it involved drastic cuts in fossil fuel use for industry, and it would never negatively impact the industrial output of the United States, and therefore impact the cost of living and lifestyles, et cetera, et cetera. And so he pulled out of that one. Then when President Biden was elected, President Biden put the United States back into the Paris Accord, so we're back in now. And it's a back and forth. You can see that it's definitely politicized. On a two-party system, it's going to be up or down depending who's on the in the White House. All right. However, because this is at the global level, at the international level, those conferences have continued to go on until 2019. And then COVID hit the scene, and the one that was scheduled for 2020 was postponed, which was supposed to be in the UK, was postponed, but they eventually mustered enough courage to do it. And so they had it in 2021 in Glasgow, all right, Scotland. And therefore, that was COP26.
So we're going to 27.
And now 27, guess what? 27 is in 2 weeks. It's going to be in Egypt now, right? Not Cairo, it's another city, but it's going to be in Egypt, and that's going to be COP27. And guess what? It's from November 6th to the 18th. So in a couple of weeks, for 2 weeks, not going, but we're going to go there virtually afterwards. Okay. So here are the last three. 25 in Madrid, then COVID hit, so 26 eventually was done in the UK. And now 27 is going to be in Egypt from November 6th to the 18th. All right. So what's going to happen is, what I like to do is, this 18 is a Friday. So I like to meet with you for the last time on the 19th, which will be Saturday, the Saturday after the conference. So we can go over the stuff that is coming out of here, all right? And this, you can align a little bit with what we saw last class with the development goals for the United Nations that were very ambitious. The first goals that were supposed to be met by 2015. Well, 2015 came and went and were not met, but then they developed more goals, double the number of goals. And the target date now is 2030, right? But it's kind of alignment with this. The development goals are aligned with these conferences that are going on the environment and climate change and so forth. So I suspect that there's going to be a lot of back and forth there on the development goals and COP27. So this kind of brings it up to date at the global level, what's happening at the international level, all right? This map here is dated, of course. This is back when the Paris Agreement was not signed, but actually published. And then it was up to each country to ratify it or not. It had to be ratified by each country individually, all right? And so you can see here that, well, ratified and then signed. Not every country that ratified it has signed it, right? So fewer. And then the ones who hadn't signed at that time was just the US and Syria. Oh, Nicaragua was also in it. Since Nicaragua has jumped on board, I believe Syria also. And of course, with the current administration, we're also in it. but it has impacted the economy negatively in the United States, and that's the honest truth. Halfway mark, at the 2-year mark, we are heading into an inflation rate here that is pretty steep, right? And so it has negatively impacted that $1 trillion budget that was passed by Congress a few months ago, is really having an impact, a negative overall impact in the American economy. All right, so there are no easy solutions, right? It's very complicated when we get the economy involved. Especially this whole thing of fossil fuels is still today the cheapest fuel around. So that's the challenge there. Okay, to end, this is my final slide for now. We'll pick up again in a couple of weeks, but basically in 2015 precisely is when Pope Francis published that first encyclical in the Catholic Church devoted to the environment. It's called Laudato Si, which is Old Italian, and it's the first 2 words of a poem that St. Francis wrote back in the Middle Ages. And it basically translates roughly to praise be you, Lord, praise be you, God, continuing the poem for Brother Sun and Sister Moon and Mother Earth. And he goes on, you know, to identify himself with the rest of creation, you know, and the benefit of creation and so forth. Is Brother Sun because he's so generous to share his light and warmth with us, and Sister Moon for keeping us at giving us good rest at night and so forth, and that's and Mother Earth for being so generous in providing food for us and so forth. That's the canticle. It's called Canticle to the Sun of St. Francis. Definitely had a big influence of our current Pope. By the way, an encyclical for non-Catholics is a document in the Catholic Church. Is the highest level of authority of a document in the Catholic Church. It's written by the Pope, but in consultation with many other experts, because of course the Pope is not an expert on biology or ecology or evolution or any of that, or climatology, right? So he depends on many, many experts that fit into that document. So typically encyclicals used to be 3, 5, 10 pages, like Humanae Vitae, for example, is about 15 pages in a small format. This now is 150 to 200 pages. So they're actually becoming books with lots of references and all that. So all this to say that they're very well thought out documents that have extensive research involved into them. But he rushed to publish this one precisely in the summer of 2015 because he wanted to have some kind of impact on the Paris Accord in the fall. It was like October. I think it was around October of 2015 was the UN conference on the climate in Paris. All right, and there was again a Vatican delegation there and everything else. So that's a kind of a seminal document, if you will, for the Catholic Church. Laudato Si. I have encouraged you to read it in the past. I continue to do that because it covers a lot of grounds, try to bring things together to that whole issue of care for our common home is a subtitle of it. We only have this planet to live so far.
I love it.
Yeah, you can download it for free, whatever language you want, directly from the Vatican Library. Yeah, okay. All right. Okay, so what we'll do then, we'll stop here, and the last date that we'll meet will be on November 19. I'm going to send you an article that just came out a couple of days ago in the BBC that talks about what is the COP, what does it mean, and what are the themes that are going to be discussed in COP27 and so forth. So I'll send you that little article for you to read, kind of preps you up, and then when the actual thing comes up, be attuned to it. It should be in the news one way or another. I know that in the United States, it's hard to get international news. And that's why what I do is I get online and I look at the BBC, which is from the UK, the British Broadcast Corporation. And you get all the British accents on it. You can just download it for free and look at the international news there. All right. Okay. No, so there's no class now until the 19th, which will be our last one. All right. So there's no class until the 19th. Do whatever else you need to do, catch up in the stats class and all that, because he's dishing it out. And for the new cohort, you have your internship that you can get involved in. All right, so everybody has something to do. And I have papers to grade, so everybody's got something to do. Yeah, I'll talk about that one. This is a couple of international conferences that I developed here over the years. Some of you participated in them, and I'll talk about them when we come back on the 19th. Okay, the 19th. This one conference in 2016 and another one in 2019. Then I was preparing for the third one. COVID hit and it's postponed, and so that one is on hold for now. But we'll see when we can do a third international conference on climate, nature, and society. So trying to bring in all the issues. Okay. Okay. Thanks again. Any parting questions or comments? Anything? No? Everybody good? Okay, so we'll see you on the 19th. Mark it for our last lecture for this course. All right? Yes, if you can come in person, it will be much better.
Thank you, Father Farid. Thank you.
Thanks a lot. Thank you, Father Dan. All the best.
Thank you.
Thank you. God bless.
Thank you, Father Stephen. Thanks again.
Thank you, Father. Thank you.
Pleasure. Father Franco. Excellent. Thank you. Welcome back. All right. Let me stop the chair.
It's Farid. Thank you, Father.
Okay. My pleasure. Thank you, Father Franco.
Bye-bye.
Welcome back.